Okay, so today we're just going to be going through lecture number 2, and if we have time we'll go through lecture number 3. So last day we began by talking about the different types of numbers, right? We started with natural numbers. We defined what those are, and then we went to the integers, and then the rationals, irrationals, and then we talk about real numbers. So we're going to continue today again and talk about some more properties of numbers, and these are the positive and negative numbers. So as we know, we can have either positive or negative numbers, right? And just be careful that the notation that's used here is when we have negative numbers, we put them in parentheses as such. That is done here, right? These are some properties here of addition and subtraction of different combinations of numbers, whether either positive or negative. So if we add two positive numbers here, number 1, we get a positive number. If we take away a number from a negative number, we get a positive number. If we take a positive number, we add it to a negative number, right? We get a negative number here, right? Because this parenthesis just denoted for this negative sign. So we get a minus b. And so 2 minus 3 is negative 1. A positive number here minus from a positive number. So the minus sign stays, right? And we also got a negative number here. Okay. So moving on. We can also multiply and divide combinations of numbers. So for example, if two positive numbers are multiplied or divided, we also get we always get a positive number, right? So that is example 1 that's done here. So if you take -2 and divide it by -4, we get positive a half, right? So what happens here is that in two negative signs here, this first one and the second one, they cancel each other out. So we get a positive sign, and so we get a positive answer. Now, if the opposite happens and we have two negative numbers, like here, then we also get, if two negative numbers are multiplied together or divided, the answer is always positive as well, which is done here. This is this one here, right? So we have two negative numbers here that are multiplied together, and we get a positive number, right? Similarly, because when the two negative signs come together, we get a positive number. And we have some video links here in your lecture slides for you to view at your own time. Similarly for this one here as well. So all of this is just a refresher, so that when we get deeper into the course, you don't make any sort of mistakes by in your computation, right? In case we get, or actually we will reach some points in our lectures where we have to do computations. So just to ensure that our answer is on the right track, we're just getting all these fundamentals out of the way. Here are two videos for you to look at on your own time if you require some more assistance. Now we get to absolute values. So the absolute value, or sometimes we call the modulus of a real number. So it's a real number. So this is why we defined all these things previously. What is an integer? What is a real number, etc. Denoted by a with these two vertical lines that encompass it, is defined by this formula here. And note also that a, whatever our real number is, right, with these two lines is always non-negative. So it's always a positive number. So if we have some computation to work out, right, let me just say a number 1 plus the modulus of maybe 2, right, in some question, then we have to define what 2 is first. So 2, according to this formula here, would be equal to 2 if 2 is greater than or equal to 0 or negative 2, if 2, I got the right E, is strictly less than 0. Right, so this is one of the definitions here of the modulus that we will use. There are variations of this that can be used, right, which we will see now. So for example here, remember we said it's non-negative always. So no matter what that's inside these two lines, if it has a negative number as is done in B here, right, it's still positive. So even though it's negative 2 with these two lines, it will always be positive 2. Look at here. Right? So negative 2 will always be positive 2. Right? So negative, if you wanted to have, let's do another example. Negative 15, same thing. It will always be negative of negative 15. And we just did previously, when two negative signs come together, get positive. Right? Now, special case here, the modulus of 0 is 0. Now, what happens if the negative sign is outside the modulus? That's different, right? Because that negative sign that's outside the modulus has no effect because the power of the modulus is inside the two lines. So like in part D here, where we have a negative sign that's outside the modulus, right? The 8 is already positive here, right? So we just keep the negative sign and put negative 8. Right? So only when the negative sign is inside, right? It doesn't matter what the number is, it's always positive. Look at E, right? So I already know that whatever is inside these two lines are positive. So this is positive 8. So I could read it in my mind as positive 8. So negative of positive 8, so it's negative 8. Right? Because the negative sign has no effect. This negative sign has no effect of what goes on inside here. Now we could combine this here and we could do simple addition as done here in F. Negative 2 plus, so the modulus of negative 2 plus the modulus or the absolute value, whichever one you want to use, of 5. So this is like 2 plus 5, which is 7. 5. So now when we have computations to work out where the numbers, more than one number is inside the modular sign, we work out what is inside first. So 5 minus 8 is negative 3. And then we take the modulus of that, which we get to be positive 3. Some more properties of the modulus, the absolute value. For all real numbers, notice that they said all. A, whatever my real number is less than or equal to always the modulus of A. This is a good example here. 4 is less than or equal to 4, right? Which is positive 4 here. And this is true because 4 is equal to 4. Now, what if the inside here is negative? Remember, whatever is inside here, the two lines, is positive. So therefore, negative 5 with modulus will become positive 5. And negative 5 is strictly less than 5. So it is true. So both of these are true. So what we're doing here is really just checking to see if our properties of modulus are correct. Here's another one. The modulus, or the absolute value of A, is equal to the square root of the square of the term that's inside. So notice that we have, let's go back, just to not get confused that we have to combine and stuff. We have the modulus here defined as this here, right? This is called a piecewise function, right? Piecewise, excuse my handwriting, function, right? Because it's in pieces, right? By definition of the word. Right? This is if you want to define the number. Then, if we are asked simply to find the modulus of the number, the absolute value, then we determine if the number is either positive or whatever negative, like we did in these examples here. And then if you are asked to find the modulus like this, then we are asked to find the square root of the square of the number, right? So for example, we have this example here. It doesn't have a number. Let's call it example number 1. If I say, right, the absolute value of 4 is 4, right? Because the modulus of this, when we put it, I use this formula here. So 4 squared is 16, and the square root of 16 is 4. So we get back this. Similarly for 9. 9 9 is 81, and we do the same thing, and we get back 81, just to check back our answer here. We can also split the modulus here, right? So the modulus of a combination of values, a multiplied by b here, right, is equal to the modulus of a multiplied by the modulus of b, right? Some people write this as a with a dot here, which is fine as well. B is equal to ab, right? Just to show that it's multiplied. If you leave it out here, it's fine as well, right? This is understood to be multiplied. So the absolute value of the product is the product of the absolute values. That's just saying exactly what's going on here in words. So like I said, we have to split them here like we did as negative. So this is like A and this is like B. And notice that we're using multiply sign here just to indicate what we're doing. So the modulus of negative 3 is 3. And the modulus of, well, 4 is 4. So think about this as 3 multiplied by 4, which is 12. I just think about it like that. Now don't get confused with this working here and what we did previously here in F, where I said that, sorry, G, where I said that we work out what's inside first. This is where we have an operation inside, like 5 minus 8. Or if we had something else like 12 plus 8 or something like that, what is the modulus of 20, which is equal to 20, right? This is where an operation is involved, like plus and subtraction, etc. This one here is different because now we have to follow this rule here in which we split the values inside and we multiply them separately, right? And then we get 12 here. So even if we want to multiply here inside, we'll get negative 12. But remember, everything inside the modulus sign is always positive. So in any case, you'll still get 12. Division as well. We can also divide here for our modulus as well. Right? So the absolute value of A divided by B is equal to the modulus of A upon the modulus of B. So for this example here, we see 4 upon 18. This is like just 4 divided by 18. So 2 goes into 4 2 times and 2 goes into 18 9 times. So we just get 2 upon 9. Okay, so this is division here. We can also combine division and multiplication as follows here. So for this one here, we just group the terms together. So 2 multiplied by negative 3. So we get the numerator here. And then we divide, right, by negative 12. And everything here is positive. So we multiply everything here first. And then we simplify here. If you want to write here, we can write 3 2s are 6 and 12, right? Or you can write it like this. Whichever instruction is asked to follow for the question. It depends on how the question is asked. So these are some properties of absolute values. So just to recap, we started on Monday with classifying the numbers themselves. Now we're going to the properties of some of the numbers continued, and where we study the absolute value, right? And we study that, and we know that we began with numbers are either positive or negative. And then all of that is used so that we can speak about indices here. Okay, and how do we manipulate numbers. So this is the beginning of lecture 3. Okay, so lecture 3 is going to talk about indices, right? And there are many properties of indices. Now we do not have to memorize or learn the properties, but we have to be able to use the properties to solve some questions, as we will do. So if n is a positive integer, right? So remember what an integer is. So if n is a positive integer, another way this can be asked is if fancy n, and then we use e, which you know from our first lecture as element of, and it's a positive integer, so we could put z plus, so it could look like this as well, right? Or it could look like this in words. So if n is a positive integer, a to the power of n, this is read as a to the power of n, represents the product of n factors, each of which is a. So a to the power of 4 is a by itself n times. So this is 4 times, right? That's why they say the product of n factors, because you multiply them 4 times. So product means multiply here. So these are the product of a n times, which is 4 times here. So if a to the power of n, in a to the power of n, sorry, a is called the base. So a here is the base. N is called the index or the exponent, right? That is what that is called. We may read a to the power of n as the nth power of a, or a to the nth power. And you will realize that this terminology in point number 3 is more likely used. And you'll see why later on, because when we have to find square roots, we use this type of English language here to denote powers when we have fractions, etc. Right? So number 3 will more likely be used. So if n is equal to 2, we read a to the power of 2 as a squared, and a to the power of 3 as a cubed, etc. But what do we call like a to the power of 4? Right? We already have a name for that, right? And a to the power of 5. So that's why we say a to the nth power. So a to the 5th power, or a to the 6th power, etc. Note that we have some special cases here in point number 5, right? This one here, very important. 0 to the power of n is equal to 0. So this tells me that n, 0 to the power of anything is 0. 1 to the power of n is equal to 1. So 1 to the power of any n is always equal to 1. So 1 to the power of 1 million, 1 billion, whatever, will always be 1. So 0 to the power of 1 million or billion or trillion or whatever will always be 0. So a to the power of 1 is itself. So again, a million, whatever, billion to the power of 1 is the same thing. Okay? So these are some special cases that we should be aware of. And it's used and as well to make our working much simpler for large values. So we reach the first of our many properties here. If n is a positive integer, we define a to the power of negative n is equal to 1 upon a to the power of n, so the reciprocal, right? Assuming here, so I forgot my comma here, comma, assuming that a is not equal to 0, because we want a value, not a as in the letter a here, right? Or I should say we want there to exist a certain value here on the denominator without getting 0, right? Because 1 upon 0 will get undefined, and then that's a whole nother story, right? For another course called 1125, which some of you may have to do because you do the special. But in this course, we just want a certain value here that's non-zero, right? Without any problem, so that we always get an answer here. So here are some examples. 2 to the power of negative 4 is equal to, according to this rule here, 1 upon 2 to the power of 4, which is 1. So 2 by itself n times, or 4 times. So 2 by 2 is 4, 4 by 2 is 8, and 8 by 2 is 16. So we get 1 upon 16. 1 upon 3 to the power of negative 3. So we could represent this as 1 upon, so 3 to the power of negative 3. This could be like 1/3 to the power of 3, which is equal to 3 to the power of 3, which is equal to 27. So the negative power as well could be in our denominator here as well. Right? If you want another example, what's a nice easy number? So instead of using 3 here, maybe the 3 and the 3 could be confusing. So let's use a different number. Let's use 1 upon 7, maybe, the power of negative 2. So 2 different numbers. Right? This is equal to 1 upon 1/7 squared, according to the rule, which is equal to, so remember, when you have 1 divided by this and you want to bring this 1 upon 7 squared here, this is to the power of 2, right? You want to bring this on top. So really, okay, let me rewrite it as 1 divided by 1 upon 1 upon 7 squared, right? Is another way you could write it. In other words, when I want to bring this 1 upon 7 squared upon here, then it's going to flip, right? So the 7 is going to be on top here. I remember from CXC maths, so this is already 1 multiply. So when I change the divide here to multiply, we flip this 7 squared and bring it on top. So I get 7 squared upon 1, which is equal to, well, 7, 7, 49, right? Or you can just leave it as 7 squared to receive 49, right? Which is what we did here as well. So when we have a divide, change to multiply, remember we have the reciprocal. We could also have a negative sign in front before. Now when we have a negative sign in front the number here, right? This is different. Now notice we have an unknown here in x, right? But it doesn't matter to us. The rule says put it like a reciprocal. So really and truly, this part here is really negative 4 by x to the power of negative 2, which is 1 upon x squared, right? So this really here is multiply. So it's really negative 4 multiplied by 1 upon x squared, which is equal to, so the negative sign remains, right? The negative sign in front of, because it's a negative sign in front of 4, you'll get 4 all over squared. Negative 4 upon x squared. So whether I put the minus sign here next to the 4, or you put the minus sign, where's my eraser? Right? Whether you put the minus sign over here by the 4, or you put the minus sign here, doesn't matter. Right? It's still negative 4 upon x squared. It's the same thing. So the negative sign either goes right here before, or it goes next to the 4. Don't put it here by the x squared, right? That is different. We could also have a combination of terms here, a plus b to the power negative 1. So everything here, because there's brackets, is to the power of this negative 1. So it comes like this here, this a plus b. Say we had 2 plus 7. And that's like 9 to the power negative 1, which is 1 upon 9, right? Which is like this. Right? So what is a combination of terms? And this 9 could be expressed as 2 plus 7. So there's 1 upon a plus b. 8 upon 10 to the negative 2. So this 10 to the negative 2, when it comes on top here, right, it will turn to, so it's negative 2. Remember, when it is negative on the flat, let's call it a flat line, right, on the regular line, and then we want to bring it underneath, then it turns to positive. So if it's negative now in the denominator and we want to go back on top, the sign will change. So it will change from negative to positive when it goes on top. So we get 10 squared. So 10 squared is 100. So 8 by 100 is 800. That's how we get this. right? So now is where it gets I wouldn't say tricky, but you just have to be able to do some practice and problem sheets and remember our rules. If n is a positive integer, so I'll write it in the language we hate. If n is a positive integer, and if a and b are such that a to the power of n is equal to b, then a, which is our base, remember, is said to be an nth root of b. So I said we'll use this terminology more, because hardly ever in the questions you'll see we use powers of 2 or 3 to say like a squared or b squared. We use more like 4, 5, and 6, etc. Right? Let b be a positive number, and positive number a such that a to the power of n is equal to b is commonly written as this, right? And this is what we call the nth root of b. This is how we read this. The nth root of b is this thing here, this. And note that this thing here is called the radix or radix, right? However you want to pronounce it. So really and truly, this example here explains this much better. So this here we read this as the third root of 2. So regular like this, we call it this is the square root of 2. But this is called the third root of 2. Similarly, if I had 2 again and I had a 4, I'll call it the fourth root of 2, etc. Fifth root of 2, and so on. So what is the rule here according to this definition before? We take whatever n is over here and we put it to the power, right, as a reciprocal. So the power here is 3, so it'll become 2, and we take out the square root sign to the power of 1/3. Right? It's easy because we're in this sort of mindset solving questions with roots that we reach a stage like here and we may make a mistake and write this as we get confused and we say, is this 9? Do I have to take a 9 and put it like to the power of 1 upon 1 or maybe 3 or something like that, right? But no, right? It's just regular square root 9 here, right? Square root 9. And if you look as well, this is 9 to the power of a half, right? Which is 3. 27 here now to the power of a third is 3. In other words, go back to the very first definition. It says that a to the power of whatever is the product n times. So in other words, what number, this is asking me here, the question is, what number do I have to multiply by itself 3 times in order to get 27? That's what this is. 3 by 3 is 9, and 9 by 3 is 27. So that's how I get this. Now there's a nice nifty function in your calculator that can work this out, right? If you want to check our answers and so on. And even so, how would we work this out if we don't know, or if we want to check, or if we are asked show working, right? I mean, we wouldn't be asked to show working, right? But like, what if you have a bigger number? What's a bigger number? Like 5, 3 is 15, 17 to 43, yeah, the power of 1/5. How will we do this before we panic? Now this is an easy question at 27, right? Like if we had another number here, like 32, right? 32. We know 4 by 4 is 16, and 16. No, that wouldn't work. All right, let's do 243 to the power 1/5, right? Let's use our brackets as well. 243 to the power of 1/5. Before we plug it in our calculator just to get the answer, how would we think about this? The technique is always take a very large number by a very small number which does not have a square root, a perfect square. A perfect square is something like 2 by 2 is 4, right, etc. And the biggest number or the bigger number that you choose between the two numbers, ensure that that number has a square root, right? So for example, say I wanted to find the square root, I wanted to get two numbers to multiply to get something, I would make sure that the smaller number that I choose, I would say we choose something like, I don't know, 5, and the next number, whatever I choose to be, should also always be the square root of a perfect square, so something like 16, because 4 by 4 is 16, etc. So in this case here, I am looking at this number 243, right? I'm seeing that's an odd number here, it ends with this 3, which means that let me choose a very small number to multiply by. What's the smallest number, the odd number to multiply by here to get back 243? It wouldn't be 1, right? Because 1 by 243 will give me back 243, and that doesn't help me with this power. And it cannot be 2 by something, right? Because we have an odd number here. So we're looking for next odd number. So the next odd number is 3. Now I said that find a large number here in order is a perfect square. So if it's 2, 3 here, a nice way to know is go in your calculator, take 243 and divide it by 3 and tell me what you get. You'll get 81. All right. And good thing for us, 81 is 9 by 9. So it is a perfect square. So that works. And then we put this to the power of 5th. Now we break this 81 down into its perfect square. So we get 3 multiplied by 9 9's 81 to the power of 1/5. And 9 and 9. So every time you break this number down, it has to always be a perfect square. 9, and what is the square root of 9? 3. So this becomes 3 multiplied by 9 by 3 by 3 is 9. So we put 3 by 3. 3 by 3 is also 9 for this 9. So we get 3 by 3. And then this is to the power of 1/5. So is it A? How many times? 1, 2, 3, 4, 5. So that means this is 3. Yeah, so this works, right? So you can check it back in your calculator. Yeah, so the answer is this. So this is a nice way to check or to find out how to break down these numbers. Always a very large number by something small. If it was even number here, I would probably choose 2 and see what number I could divide by in order to get a perfect square in a calculator, right? Or you could just do it shorthand and just use your calculator and get the answer, right? Which is what most people will do. But that would help us at the end of the section, right? The end of the section is where we have to actually solve for this index here, which we don't know. So it's good to develop techniques like this. Right, so moving on, let b be a negative number, then the nth root of b is a real number if and only if n is odd. So that means really I'm concerned with this number inside our square root sign here being negative. So in other words, we find in the nth root again of this number. So the nth root of 8, if you think about 8, 2 by 2 is 4, 4 by 2 is 8, right? But this, we are saying that in that case, the nth root of b is a negative number, right? If it's what is inside here is negative, because negative 2 by negative 2 is positive 4, but positive 4 by negative 2, because we have one negative 2 remaining, will be negative 8. And similarly for this example here. More properties. If m and n are positive integers, we define a to the power of m upon n. Now this is different from before. Before, we have b to the power of 1 upon n. Now we have a, or same b, to the power of m upon n, right? So m and n here now could be two different numbers. And the m, the numerator, always goes inside, and the denominator always goes outside for the nth root. Assume a is greater than or equal to 0 if n is even. So 4 to the power of 3 upon 2 is 4. So we put the numerator, which is 3, inside, and the denominator is outside. But remember, this is square root, so it's already 2. So I don't need to write a 2 here. If this was another number, like 4 to the power of I don't know, 7 upon 3 or something like that, then this will be 4 to the power of numerator inside, denominator outside. It will look like this, right? So this is 4 cubed, which is square root of 64, which is 8. Right? So similarly for 27, numerator inside, so 2 inside, denominator outside, so 3. So this is the third root of 27 squared, right? Which you could all put in a calculator if you want, and you'll just get 9. More rules. If m and n are positive integers, we define a to the power of a negative m upon n is equal to the reciprocal. So it's like the very first rule. The only difference is now that we have an m here, an extra number, right? Which makes it a little bit more tricky. But the rule is still the same, right? The numerator, look at this example here. The numerator, which is 2, goes inside, and the denominator here goes outside. And then we work this out. And in most cases, the number that we have given here will work out like a whole number here, like 4, a natural number if you want to call it. X to the power of negative 5 upon 2 is 1 upon x to the power of 5 upon 2 using this rule. And remember, the 2 is already square root, so we don't need to write 2 here. So just write x to the power of 5, right? And we already defined what a to the power of 0 is from before. So anything power 0 here, we get 1. So it doesn't matter what's inside the bracket here. Right? So that's how we get 1 by 1, which is 1. And this here, we'll explain this more. This will make more sense when we reach the end. More rules. If r and s are real numbers, then a to the power of r by a to the power of s is equal to a to the power of r plus s. So in other words, we just add the powers. Right? Notice that we have a here and we have a. Right? This tells me that the base must be the same for me to add powers. So if I have 3 to the power of 4 multiplied by 3 to the power of 7, that is obviously 3 to the power of 11. But if I have 3 to the power of 7 multiplied by 4 to the power of 9, I can't add this because the bases are not the same. 3 and 4 is not the same thing. Right? So the a's have to be the same. The bases must be the same. That's what this is telling me here. Right? Notice that we can also add fractions as well. Right? Everyone here can add fractions from CXC Maths. A third and a 6 is a half. But remember, anything to the power of half is just square root. Okay, we could also have negative power. Now notice here in this example, 3, 3, 3. All the bases are the same. That is the only reason I can add the powers here. Right? And these two examples here are some general cases of adding indices. Now, if r and s are real numbers, another rule, a to the power of r brackets by to the power of s is a to the power of r of by s. So in other words, you multiply the indices. So when they are separate here, you add the powers. When they are together like this, you multiply the powers. 4 3s are 12, like in this example here. 1/3 by negative 3 is 5 to the negative 1, right? Because remember, this 3 will cancel with this 3, and we have our negative sign here. So that's how we have our negative 1. So you have 1 upon 5 because it's reciprocal. Very first rule, right? B to the power of negative a, or I think we use a to the power of negative b, whatever it is 1 upon this, right? Again here, just multiply the indices. Very simple. 5 by negative 4. 5 4 is 20. Well, negative here, so negative 20. And these examples here are more for you to read. Division now of indices. When we divide, we minus the powers. So basically, when we multiply the powers, we add them. When we multiply here, right, the bases, we add the powers. When we have this case here where we have parentheses, we multiply the powers. And when we divide, we subtract the powers. Right? Numerator minus denominator. If a is not equal to 0. And we don't want it to be equal to 0. And it won't be equal to 0 for this course. Because we want a solution. So 2 to the power of 6 upon 2 to the power of 4 is 6 minus 4 to the power of 6 minus 4. Notice again, this a and this a must be the same. In other words, the bases must be the same. I make that point because when we have to solve for x, we can't have different bases, right? And all of these examples here are for you to look out. It's very straightforward. It just follows the same process as before in the other examples. This here is an extension of the second rule where we have a to the power of r parentheses to the power of s, where we multiply them. In this one here, everything inside the parentheses is raised to the power of r. So for example, 2 by 3, I notice that we have the dot inside to denote 2 is multiplied by 3. We take the power of each one separately and we work it out. Similarly here, this is 2 multiplied by x. So the x also has to get x to the power of 3. Right? So you see how all the rules are starting to come now. We have 3a to the power of negative 2. This is to the power of negative 2 as well as this. Right? And these are all examples here for you to read. In a similar way, when I have everything inside here to raise to a power, and I multiply here, right, and I bring everything to the power, whatever the power is, right? When I divide, I can do the same thing. Everything that's inside goes to the power as well. So a to the power of r, b to the power of r, and we work it out separately. So 2 upon 3 to the power of 5 is 2 to the power of 5, 3 to the power of 5, and we work it out. Right? Whatever this is in our calculator. X squared upon y cubed all to the power of negative 3, where we had to use the rule from, where is the rule? This one here, a to the power of r by a to the all to the power of s. We use that rule here. So 2 by negative 3 is negative 6. 3 3s are 9, and then we work it out. Right? So we use that rule. Or there's another way you could do it. Right? And you'll get the same answer. This method here is easier one, right? Because we use the rule from before. This may second way, which I just put, may prove to be a little bit tricky. This is a further example here involving quotients and where we have square root signs. So we combine the rule, the nth root rule from before, right? Where this is, so it's 3, so we come up to the power of a third, and then we make use of the rule that we just did here to multiply the powers, right? And that's how we get this. So a to the power, so everything goes to the power, right? Another way you could write this to make it look a little bit better is that we separate a to the power of 1/3 multiplied by x to the power of 3 and upon 3. And then we write the denominator in a similar manner. We use brackets, right? Should have really used brackets here. Suppose to use brackets. Then this 3 will cancel with this 3. That's how we get x to the power of n. That's this. And a to the power of 1/3. So what number I have to multiply by 3 times in order to get back 8? Well, that's 2. And same thing for 27. That's 3. Right? So when we do more questions and examples, we get accustomed to knowing these squares and cubes, etc. So we don't have to constantly go to our calculator for it. This is also a special case here where a upon b to the power negative r is the same thing as negative 1 by r. Because remember, every negative number has can be split up like this. So negative 2 is the same thing as negative 1 multiplied by 2, which is negative 2. So that's what we did here, right? And what we do is with the negative 1 here is we use the very first rule, right, the second case of it, and we flip this, right? So the b comes on top and the a goes behind, and then we have everything to the power of r. So a upon b to the power of negative r is the same thing as b upon a to the power of r. So this becomes convenient when we have negative powers and we just want to flip them. Aha, now we reach where we really, all the rules from before, this is where we're going to use them. If r and s are real numbers, then a to the power of r, already supposed to have then a to the power of r is equal to a to the power of s implies that r is equal to s. And we could even do a biconditional and say if and only if, right? Because if this happens, then this happens, and if this happens, then this happens. But once again, notice that the bases must be the same. And I make this point over and over because what this is telling us is that we have to solve for r and s now, right? For example, 3 to the power of x is equal to 3 to the power of 2. So the bases are the same here. So therefore we can equate r and s, so x is equal to 2. And that is true because 3 squared is equal to 3 squared. Look at this one here. 3 to the power of x is equal to 27 to the power of 2 minus x. Now this is not the same like this. So now we have to express 27 in terms of the same base. Now it's always a dead giveaway what we have to express it as, because look, the smaller base is always here. So I know this is 3, 27 is 3 to the power of something, right? In order to get it to look like this. So this can be expressed at base 3. So 3 cubed is 27, 3 by 3 is 9, 9 by 3 is 27. So I can rewrite this as 3 to the power of x is equal to 3 cubed. So it has to be like 3 cubed multiplied by 2 minus x. And now we can take this rule here. Where's my rule? This one here. A to the power of r parenthesis to the power of s. And we can use it here. And multiply this. And then solve for x, which is what we're going to do here. Right? So this is where we use. So all the rules are going to come back. So 3 to the power of x is equal to 27 to the power of 2 minus x. 3 cubed. We multiply 3 by this. 3 by 2 is 6. And 3 by negative x is negative 3x. So now the bases are the same. Right? And the point of multiplying all this is just to have it in a nice linear form here in order to solve for x. So x is equal to 6 minus 3x. So this implies that, well, I could take this 3x here and I could bring it on this side as negative 3x. So negative 3x becomes positive 3x. So x, so it becomes x plus 3x is equal to 6. Then we have this. And so we have 4x is equal to 6. So x now is equal to 6 divided by 4. So I divide by 4 on both sides to get rid of the x, the 4 on this side. And 6 upon 4 is 3 upon 2. And this is my answer. This is how I go about solving, right? So the point of all the rules from before is to reach this point here in order to solve for x, right? And we have one difficult, not so difficult example here, which I will save for class, and you can go through it and you can look at you can begin to look at the problem papers and see which questions resemble this format, so you could begin to try and solve them on your own. Okay, that's it for today's video.